Thank you. Okay, the last speaker will be Mingjia Yin. She received a BE degree in electrical engineering from the Nanjing University of Posts and Telecommunication, Nanjing, China in 2011, and the MSc degree in wireless communication from the University of Bristol, UK in 2012. She is currently pursuing the PhD degree in electrical engineering with the School of Electronic and Electrical Engineering, University of Leeds in the UK. Her current research interest includes power systems operation and optimization. Let's listen to Mingjia's presentation. Okay, Natalie, can you please share the video? Thank you.
Good afternoon, everyone. My name is Mingjia Yin. I am a PhD student from School of Electronic and Electrical Engineering of University of Leeds. I'm very glad to share you my work about the integration of soft open points to enable the flexible operation of microgrids. Since the last decade, there are plenty of advanced active components have been designed and applied in the power system. For rural areas, the widespread use of distributed general energy resources, such as the distributed generation, energy storage, and controllable loads, is anticipated in many countries. This also leads to the operation problems, including exclusive fault levels, also the violations of thermal and voltage limits. So my work is to investigate the accommodation of the active components to flexible the operation of microgrid and also to the utility grid. One of the components considered here is called soft open points. I will introduce it laterly for the details, and also consider the distributed generations with active and reactive capabilities. Usually, the network in a microgrid is a radio configurations connected to the utility grid in a PCC. However, these ratio configurations will induce the possibility that the power flow will be unbalanced at different radio feeders, as there are different loading conditions in different feeders, especially when there is a very high penetration of intermediate like wind power or solar power, and also the flexible demands. All of these will return leads to a very high power losses, and also increase the peak currents and undesired voltage excursions. So the performance of these units and SOP will formulate a very complicated and highly constrained optimization problems because of the non-convexities, non-linearities of the power flow equations. Many materialistic algorithms now are very popular for handling such kind of problems in the power systems. In this work, I will use a fast covariance matrix adaptation evolution strategy with an increasing population size method. And also the main objective for the problem here is to minimize the power losses. With the control of power flow, it is expected that the voltage profile will be better and the line congestion problems will be relieved. The figure here is a brief description of the SOP. It shows a two feeder ends network interconnected by a bank-to-bank voltage source converter-based SOP. Both VSC view their own waveforms with desired amplitude and phase angles. This allows a full control of active power flowing through the DC link, as well as an independent reactive power supply and absorption at both interface terminals. So the controllable capabilities enables the SOP operations in normal network operation conditions. It can also provide the instantaneous and independent voltage control mode and the isolation for distribution and faults. But this is beyond the discussion of this work, so I will mainly focus on the normal working condition, power flow control conditions. One of the VSP works in that mode works with the PQ control scheme, and the other operates in the DCQ control scheme, so it can provide the both active and reactive power at both terminals. Here, the PSOPM and PSOPN is the active power at SOP entering the two feeder ends at bus M and N. And also the PSOP loss is the loss of this SOP for a high efficiency one. The loss will be very small and can be neglected. So it could be used zero in the study. And for the reactive power outputs of SOP, they are independent and can be positive and negative, which implies the power compensation and absorptions. So the SOP is used to place at the feeder ends, and it replaces traditional high-line switches, also called the open switches. It configures closed-loop configurations, which is advantageous over a radiational one because the load can be balanced between the different feeders, and it will also have better voltage profiles and improve the reliability of power supplies. But such looped configurations also increases the risks of the wide area failures. So the isolation capability of SOP can mitigate this banks. So that is why we consider such a configuration which is better than the traditional ones. The experiment design and associated method is shown as the flow chart. The first step is the data collection and network structure choice. The next step is in this work, so we use modifying IEEE 33 bus system, and it's a radio structure. The basic load is 3,715 gigawatts and 2,300 kilowatt. The main body, the next step is the main body of this work. It determines the optimal locations of the DG with the SOP. We use fast IPO PCMAS algorithms algorithms inherits the merits of evolutionary strategy. It uses weighted recombinations of parents to generate offspring through the adaptive covariance of a matrix. IPOP here means the increased population size. So it will trigger a new start by increasing the population size. The population size. Further fasten the algorithms. Historical best candidates will be part of the offspring. So every time a candidate is generated, use a power flow solver to check the feasibilities, and also to check the voltage constraint and branch current constraints that will guarantee the physical operation of this network. The result of this optimization will be the bus numbers, capabilities, power factors of distributed generation, and it will also provide the generated or the absorbed power at both terminals. So the results of this study will be considering 5 different cases with different numbers of DG, with or without reactive capabilities, and also with or without SOP. So the result is evident from the following aspects that the table shows. It is the proposed algorithm is superior than the traditional GA and MPSO algorithms in finding the optimal value in all 5 cases. For example, in case 5, it reaches total power loss 14.33 gigawatts, which in base case is 212.5 gigawatts. The reduction is 93%, but it is at the expense of the computational time, as it is the planning problem now. So the computational time is not very important stage. Also, we will see that the reactive capabilities of DG units contribute to the better energy use. By introducing the reactive power, the system power loss reduces from 115.5 gigawatts in case 1 to 78.81 gigawatts in case 2. So, and also there is a very significant improvement on the transmission line congestions. The power line loss, the powers under the allocations of 1 DG with several different SOP capabilities is different. When SOP capability increases, the power loss will gradually reduce. For capabilities above 600 kVA, the reduction of power loss can be ignored. So in the work, we set SOP capabilities to be 600 kVA. And also we considering different numbers of DG, the DG numbers. The advantage of introducing more DG with SOP is evident. The voltage profile and additional DG units associated with the SOP improves. So in conclusion, this study prevents a novel algorithm called IPOP-CMAS for solving the optimal DG allocation problem with SOP. Compared with the 2 popular optimization algorithms, GA and MPSO, the proposed one has the best optimization performance at the cost of computation time. The proposed algorithm is validated on IEEE bus microgrids, and different factors are evaluated. It reveals that the capability of SOP is negatively correlated with the power loss. And as expected, the reactive capabilities of DG with SOP applied will enhance the system performance. The algorithm can be applied to the practical cases involving probabilistic load models. So further works will be dedicated to the cases considering the load dynamics and the optimization problems. That's all my work I would like to discuss today. Thank you very much for listening. If you have any questions, you can ask me now. Thank you a lot.
Okay, thank you very much, Mingjia. Can you hear me?
Yes.
Thank you very much for your nice presentation. I have a question about constraint handling in your proposed solution approach. How can you evaluate satisfaction of all your constraints after solving the optimization problem?
So in my work, there are three groups of the constraints. One is the power flow, and I have used the back-forward sweep method to guarantee the power flow of the network. And another one is the voltage constraint. So it will be defined as the minus and a positive and minus 5 of the voltage, the rated power. And also another one is the current constraint, and that also need to be below the one of the designed value. So after I run the power flow solvers, it will get a result, and then the result will be checked to see if the voltage and the current is beyond the constraints. Once it is outside the feasible region, so the solution will be discussed, and then we will generate a new candidate solutions for this problem. Run it again. So this is basically the things of the metaheuristic one method, or metaheuristic method to solve a question like that. Thank you.
Okay, thank you very much for your excellent presentation and also answering to my question. Okay, it was the last talk in the CRESM HiRes workshop. Thank you for attending the virtual CRESM HiRes workshop.